Hi, this is Dr. Nick from the ECG Academy, and this section is about the AV node and the kinds of things that can go wrong with it, otherwise known as AV node dysfunction. We're going to be talking about the different kinds of AV block that we can encounter, and I have to tell you, there's a lot to this, and it's kind of interesting because a lot of the books don't really get into the nuances of AV block, the different types. There's a lot of misunderstanding out there, and my plan here is to try to get you guys to understand this thoroughly. Let's just start with the idea that you have muscle cells, of course, and if you remember, cardiac muscle cells are capable of depolarizing, and for the most part, sodium rushes into the cell, which causes the cell to go from a negative voltage on the inside, depolarizes the cell, so now the inside of the cell is more positive because you've got all these positive charges that have just gone into the cell. And then potassium, which is the predominant ion inside the cell, sometime later rushes out, basically restoring the normal resting membrane potential by making the inside less positive, going back to the resting membrane potential. Well, when depolarization occurs mainly through sodium rushing into the cell, we call it sodium dependent. Sodium-dependent cells, characteristically the atrial muscle, the ventricular muscle, and the Purkinje system, and they're recognized by this rapid upstroke. This is known as phase 0, and then we have 1, 2, and phase 3. Phase 4 would be diastole, when certain pacemaker currents will allow certain cells to depolarize spontaneously. You know, all the cells in the heart can depolarize spontaneously to some degree. So those are sodium-dependent cells. But if you notice that the SA nodal cells and the AV nodal cells, the action potential looks a little bit different. They don't have a very rapid upstroke of phase 0 during depolarization. The slope or the rate of change of the voltage is a little bit decreased, and you can see that in AV nodal cells as well. And that's because there are less rapid sodium channels in those cells. And instead, what you have is calcium channels that allow calcium to move into the cell during depolarization. Calcium currents tend to be a little bit slower. And so sinoatrial nodal cells and AV nodal cells are known as calcium dependent. This becomes important because they behave differently. We will talk more about this in the advanced physiology video, discussing the differences between calcium-dependent and sodium-dependent cells. But let's just say, for the sake of understanding the AV nodal physiology, is that the signal takes a little longer to get down the AV node than in other parts of the conduction system. If we bring up our video animation here, you can see that the atrial depolarization spreads rapidly, but the AV node there hangs the signal up for a split second. So there's a little bit of delay in the conduction through the AV node, and this becomes important in understanding what happens when the AV node is incapable of conducting every impulse. Okay, so let's just get rid of this for now, and we're going to talk a little bit about the structure of the AV node. Okay, even though we draw the AV node as sort of a compact structure, it's very complex. And if you look at it under the microscope, you can see there's quite a crazy architecture going on, but it's basically located in the septum of the atrium. So here's the left atrium on this side, the right atrium on this side, and the ventricular septum is here. And the AV node, as you know, is connected to the bundle of His fibers that plunge through the central fibrous body and then split up into the left and right bundle branches. There are specific AV nodal cells known as N cells. This isn't too terribly important, but I want you to understand that there are also transitional fibers. These are long cells that extend out into the atrial myocardium, and they kind of funnel the atrial signal into the AV node. So as the atrium depolarizes, the signal is led into these transitional fibers and enters the AV node, where it then gets delayed. Just so you know, there are other fibers that can enter the AV node at other locations. In fact, when we start to talk about certain kinds of rapid heartbeats, we'll touch more on the role of this slow AV nodal pathway. But for now, let's just ignore the fact that there may be multiple fibers going into the node. The AV node, as I said, delays the signal for a split second, and then the signal rapidly emerges out the other end and goes down the His-Purkinje system into the ventricles. So how do we assess the state of the health of the AV node? From the outside, there's not much you can tell other than simply measuring how long does it take for the signal to go from the atrium to the ventricles. And that gives you a rough idea of the health of this AV nodal conduction system. How do we measure that? We measure it on the surface ECG as the PR interval. Remember, the P wave represents atrial depolarization. The PR segment is usually a flat area that you can see after the P wave and before the QRS complex. The Q wave, this is a nice Q wave here, which is a downward deflection. The R is the upright, and the S is a negative deflection after the R wave. And then, of course, you can see the T wave. There's an ST segment here that we'll talk about in future lessons. But let's just talk about the P and the PR interval. Where does the P wave start? It starts where the P wave just leaves the baseline. Where's the baseline? Well, that's the segment that's in between the previous T wave and this P. Now you can see in this ECG the baseline does drift a little bit, but you can get a sense that right about here is where the P wave begins. And right about here is where the QRS complex starts. Now with some practice you can eyeball these PR intervals, but the best way to do it now at this stage of the game is to use a pair of calipers. So let's bring our calipers over and we'll put the first point right where the P wave leaves the baseline, and the second point we place right where the Q wave starts, where the QRS complex leaves the PR segment. Then we'll take our calipers and put the one point on a heavy line, and we can measure number of milliseconds. Remember, each 1 millimeter small box is 40 milliseconds, so you have 40, 80, 120. This would be 160, but it's like 3/4 of a box here, so you have to call this 150 milliseconds. So the PR interval is 150 milliseconds. That's normal. The normal PR interval should be 120 to 200 milliseconds. That's the normal PR interval. When that interval is outside those rates, then you consider this an abnormality and you can make the diagnosis accordingly. Now, what you have to understand is that under normal circumstances, every P wave is followed by a QRS complex, and that you have what we call one-to-one AV conduction. That means the AV node transmits each atrial signal that it receives down to the ventricles, and you have this kind of normal QRS morphology with a P wave followed by a QRS complex. Okay, but when there are problems with the AV node, one-to-one conduction may not exist anymore, and some of the impulses may not be able to reach the ventricles. This is a condition known as AV block, or atrioventricular block. Now, there are different degrees of AV block, which I'll review right now, and we'll cover each and every one of these in a separate video. Now, the way you have to sort of first approach this classification system is to understand that there are 3 different degrees of AV block. There's first, second, and third degree. The easiest way to kind of get your brain wrapped around these is to first understand that in first degree AV block, all the P waves conduct to the ventricles. It just takes a little bit longer. Now, down at third degree AV block, that means that none of the P waves are conducting to the ventricles, and the ventricular rhythm has to be some kind of escape rhythm, which we touched on in our discussion of sinus node dysfunction. Second degree AV block simply means that some of the P waves are conducting, and we're going to have a long discussion about the different types here, but since some of the P waves conduct, obviously that means that some do not conduct. And that's how you can diagnose second-degree AV block, which indicates a partial failure of AV conduction. Now that I've introduced the classification system of AV node dysfunction, go ahead and watch the rest of the videos in this section. You'll be able to understand all the nuances of this very common electrocardiographic diagnosis. So for the ECG Academy, this is Dr. Nick. Thanks for watching.